Very, very pleased to introduce the third of Peter's lectures tonight. We've heard about the history of life on Earth and all sorts of mass extinctions, and we've heard about the possibilities for life on other planets. And today, Peter is going to talk to us about aliens, which will be exciting. We at the Princeton University Press, we've had a long association with the university in co-sponsoring these public lectures and producing books out of them. In 1921, Albert Einstein came to the United States for the first time and gave 3 lectures at Princeton, and we turned them into a book called The Meaning of Relativity, which was a bestseller for the press and has been for the last 80 or so years. And since then, we've brought in scientists like Sidney Brenner, Martin Rees, Walter Alvarez, Andy Knoll, a whole bevy of some of the great living modern scientists. And it's an exciting thing for us at the press to work with the university to bring in great scientists, hear some great lectures, publish some great books. And Peter Ward is a fantastic geoscientist, a biologist too, and a great astrobiologist, one of the founders of that field. And he's also a superb expositor of science for a general public, and very excited to help bring him here tonight. Peter.
Thank you. I have to turn my little thing on. I promised I would show up in a white suit, and here it is. Last year I was invited to the University of Miami to give some lectures, and I ended up going down there without my one sports coat. And my very ancient host said, "You absolutely have to have a suit," and he put me in a South Beach hotel. So we went suit hunting, and this is all there is. So I got up and I gave my lecture, and I felt so good. It was Miami. It was perfect. And somebody from the crowd said, "It's Colonel Sanders." That's no fair. So tonight, let's finish up. I want to talk about aliens. And certainly aliens are something that any of us who ever turn on the TV, I don't think you can turn on the television any given night without seeing aliens somewhere. The movies, of course, are absolutely filled with them. I saw that James Cameron, the author of Titanic and other movies, is again making a huge $200 million blockbuster called Avatar, an alien movie. So we have this in our consciousness through all the popular media, at least, that the universe is filled with other intelligent beings. The sad truth, of course, is that we have yet to discover anything except Earth life. So tonight I'd like to talk about what life on Earth really is and ask, what might not Earth life be like? And the scientific community has really come up with 2 terms. Instead of aliens, nobody wants to talk about aliens because there's a certain nasty connotation about aliens with the no necks and the little pencil eyes and the little round heads and things. That's what you think when you see alien. Well, alien to many of us now is going to be a bacterium with a somewhat different chemistry. So the 2 different terms have come about. The National Academy of Sciences had a panel looking at this. It's called the Weird Life Panel. And so weird life is one way, but the other one is a very nasty long term, but it really sets the stage. Life as we don't know it, which sets it apart from life as we do. So tonight I want to talk about life as we do know it, what life as we don't know it might be scientifically plausible, and then ask some questions about perhaps maybe the frequency of stuff out there. Well, certainly the greatest instigator to believing that indeed there must be other life in the universe is this picture. Can we bring the house lights down a tiny little bit for this? This is one of the most famous of all Hubble pictures. This is the deep field, the Hubble deep field. With everything you see on here is a galaxy. These aren't stars. I mean, these are galaxies, 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 galaxies. Each, conceivably, with hundreds of millions to hundreds of billions of stars. And so this is where Carl Sagan wasn't wrong. He got castigated for the billions and billions. But you can't look at this without sort of getting into trillions and trillions. It comes off the tongue easier. The universe, then, is many, many, many galaxies. In each of these galaxies is many, 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 many stars. And I think all of us just delight, I think, in this vision that what really, if you're a logical person, how could we be alone with a single galaxy having so many abodes, potential abodes for life, and then multiplied this by billions themselves. So the numbers are so overwhelming. I cannot conceive of a universe where we do not have any more life. We have to have a universe teeming with life. And so in that spirit, you can turn the house lights up a little bit. Let's look at this. But let's type in alien on Google, which I did. Alien image. I just started picking them off one by one by one. And the sad thing is I'm such a Luddite, inept fool that actually 3 or 4 of these guys were little movies, and they wave at you and shoot ray guns and do all the great stuff that aliens do, of course. And the interesting thing is that, I mean, it looks like the same species has colonized the galaxy. Now, except for this snail guy, and of course this poor rotting creature from Russia, they do look, you know, you've got these drawn up eyes and they've got those silly necks. Now, this is an interesting thing. This painting, the Madonna with St. Giovanni, and in the very top circle I circled there, this is the first picture of a UFO in history. So that painter clearly knew about aliens, so we're all the way back in the Middle Ages, and then of course we have the aliens that we found up through here, and this is a famous Russian picture of a sphere that fell from space. And of course, who could forget Roswell? And in fact, as I got home from having dinner at one of the dorm houses, last night it was this restaurant, tonight it was a dorm. It was interesting. I've been here 3 days. I see what happens through lectures. And there was Discovery Channel, and there was Roswell again. You just cannot get away from it. So it pervades popular culture. And why is it they're humanoids always? And why don't they have any muscles in their neck? Biomechanically, this head would flop over, and it's not going to work. So to talk really scientifically about this, we have to do a couple of things. We just do some bookkeeping. Let's really, do we need a definition of life? And we do. And there are a number of ways that you can do it. In history, historically, these are the ways that life has been identified by groups that we could identify as Darwinists, many examples. I'll give a few examples except for this, but there's metabolists, thermodynamicists, Schrodinger, the first physicist to really start thinking about biology in a meaningful way. And this is a great breakthrough. Physics wasn't really concerned with that. 1944, famous paper and book. Biospherists, thinking about biospheres, and of course the Santa Fe Institute, complexity, and there's others as well. But there's a number of ways now you can break it down. But Schrodinger's quote, I won't bore you with too many quotes, but this one's really a very interesting one because it's so moved away from anything up till that date about what life might be. And Schrodinger defined life in terms of its energy and what it was doing with energy. And he came up with this great quote. It feeds on negative entropy. Entropy is my office desk. It's the desktop of this computer. If I turn around, it completely goes entropic, fills up with stuff. Negative entropy is order. So life is making order. And he said it does it by feeding on negative entropy, whatever that is. It's as if a new property in the universe. We know what entropy is, but here he's talking about negative entropy. Let's quantify that. Very interesting point of view. Overtly eating, drinking, breathing, blah, blah, blah. So this was a really great sort of change from what had been done. Many times the evolutionists, but the evolutionists now have added something different as well, self-sustained chemical systems. But their addition to this now is that it undergoes Darwinian evolution. Survival of the fittest. Too many are produced that can never live. Some are going to die. They're going to pass on genes. Natural selection, and they're going to change through evolution. That life, an inherent property of life to this group of people is that they evolve. This is interesting too. This is as different and as interesting as Schrodinger's point of view is. And here we see something really different from this energetic point of view. So let's get away from definitions and just ask ourselves in a common sense sort of way, what is it you really need? And here now we are defining life just by going through what we think are the various components. A membrane. Why a membrane? Because you need to separate life from non-life. It's not everywhere in this hall. It's encapsulated in each of you, which has a membrane. And if any of you sneeze, lots of tiny life in tinier membranes and the stuff that we carry with us. So we've got lots of life in this hall. And every bit of it is closed up in something. And every bit of it is metabolizing as we speak. There's machinery going in there because you have to constantly work to stay alive to keep that negative entropy. If you don't do that, you die. It's amazing how much energy your body uses just sitting here listening to a boring lecture. You're burning up far more energy than you can think. And we have to constantly do this our whole lives. It takes a whole lot of work and a whole lot of food. Now, here's a little thought experiment I ask my students. I ask them, I want you to think of every cheeseburger you've ever had in your life. How big a building would you need to fill it? Put it in there. And we're talking some giant buildings. I've got really some major undergrads. Think of all the food we've eaten in our lives, each of us. That's a huge amount of material that goes through us to keep us alive. And then multiply that by the water you've had to drink, the air you've had to breathe, the vitamins you've had to take. We are these little machines that are perturbing the earth, the atmosphere, the water around us in phenomenally important ways. We are chemistry sets. The metabolic machinery requires chemistry. We are information systems. We have to tell the chemistry how to work. And we have to reproduce. So now we see another definition of life based on what the pieces of it are to make it work. So one of the really interesting controversies is still the evolution of the first life on Earth. And tonight I'll throw out a couple of the newest ideas that come out of the astrobiology revolution. But we should really start with Darwin. One of his tenets of his book was that all life came from a single source. There was some first living cell. And as many of you know, you can learn an entire college education about science. All you ever have to do is watch every Star Trek there ever was. The whole lecture is going to be there somewhere. And I saw Picard go back to the first life in some little ugly pond. And I think he fell in it or he stepped on it. He killed it somehow. That fool. And that was Darwin's idea. And this is right out of Darwin. There was Picard doing Darwin's warm little pond. And that first life was hanging around in there. And the stupid fool walked on it. Well, that's what Darwin thought. He really did think it came from a small, warm little pond. And his sense of how it looked, this is a diagram, was that it started here, A, and that the entire world and everything in it came from one first individual. Now, we believe that every bit of life on Earth had some single first originating cell someplace way back when. But we're not sure anymore that all of the life on Earth is indeed related. We're up here somewhere to this. In fact, we cannot say that there are not aliens on this world right now. So we're going to define what Earth life is pretty soon. And then make the statement, and this has been made by Jonathan Letterberg years ago, Nobel Prize winner, that it's certainly possible that there may be alien life. And in fact, a large institute at Arizona State has just been set up, bringing Australia's best astrobiologist here, giving him a lot of money to go looking for aliens on Earth. And that process will begin. Characteristics of Earth life, nasty slide, but it's not simple life. Water. Water is essential for active life, Earth life. Our life is contained in a cell, and our life is carbon-based. And then 3 has a whole bunch of stuff, and this stuff actually is important. We're going to come back to it. We have nucleic acids, consisting of 4 nucleotides. We have dual nucleic acid system, both RNA and DNA. We have proteins. Now, this is the really interesting one to me, and we're going to come back at this. All Earth is united by the fact that there are hundreds of amino acids. These are chemical molecules out there. But all Earth has the same 20. Now, why do we use that 20? Why that 20? And why not 21 or 50? But why the same ones over and over and over and over and over? Is there a functional explanation? Are these the 20 best for building proteins? There's something about those amino acids that builds better proteins than other amino acids. Is there something that deals with energy? They react in these chemistry sets in better ways. And we have no idea why this is. This is a fundamental property of life, one of the great questions. We know that we have very similar types of cell walls. We use lipids that are quite similar. We use very similar energetic systems at a basic level, that we use some basic chemistry. So our carbon-based life does this stuff. We know that our life replicates, and we know that our life evolves. So we're going back. Earth life, again, has to have this. It's a subset of all the definition of life stuff we did. It's got all that stuff, but it's got this big middle. We're going to look at that big middle for a minute. So let's think about Earth life and define it now. Our Earth life has to use DNA. It has to have a specific genetic code. It has the same 20. And according to biology texts, it's always cellular. And therefore a virus, I teach biology, a virus we teach is not alive. And I think this is nonsensical. I think it's absolutely chauvinistically nonsensical. I removed this. I would say Earth life can use DNA or RNA. I would say the specific genetic code is certainly there. We're certainly using these 20, but guess what? Scientists are now making bacteria that use 21 or 22 or 23. They're substituting. We're making aliens. We're making life that isn't cellular. Cellular, the definition being the lipid code around here. A virus is simply a cell that has a protein coat, not a lipid coat, but we don't call that a cell anymore. So DNA is a really interesting molecule. It's very complicated. We know this beautiful double helix, hugely complex. How did DNA first come about? And this becomes the biggest problem in the origin of life scenario. You've got a bunch of chemicals out here, and you've got some little assembly area over here, and you get a martini mixer, right? You put them in and shake them, shake them, shake them, and this is what comes out. Now, talk about the infinite number of monkeys in Shakespeare. I mean, you've got to do a lot of shaking of the chemicals to make this come out of it. And this has always been what the creationists say. This is way too complex. There's no way you could ever build that de novo. It's too complicated. It would have had to been designed. So we'd like to know a lot about DNA. And interestingly, lots and lots and lots of information about DNA is coming about. And the questions that I've asked some of the people at my school and that I'd like to know is one of two possibilities to me. It could be the DNA, the one we have, got there first. That we had a bunch of proto-DNAs. They didn't work very well. But when we got this finally nice type of DNA, it just took over the world because natural selection, it worked better. It's the first out of the gate. But maybe we had this battle among lots of different kinds of DNAs because there's many different ways you can make DNA. And chemists are doing some fantastic things. A group, part of the NASA Astrobiology Institute, made 6-sided DNA. They're making totally different language DNA. They're building DNA that has a code system radically different than our own. And it works. It doesn't have to be the way ours is. We don't know if it works better. So DNA, the one we have, might just be one of many different ways that could have been there early on. And the second and more interesting question, why is it that every one of us and every bit of Earth has the same genetic code? That doesn't seem to make sense to me. Because you would think evolution would make, in some specific case, this code works better, or maybe this code. And if we had lots of different life, how did they all get unified into this single thing? And I think it's the viruses. And people are increasingly thinking that viruses made the most important evolutionary process in the early Earth. And I've proposed that viruses are actually the key to the evolution of life on Earth. Really the key, because they could get into little protocells. And they took pieces of information and stuck them in little metabolic cells because they had the keys of the kingdom to get in and out really easily. Tiny little particles with a little bit of DNA, and I'm just going to inject this in you. Viruses are parasites. Parasites are alive. A virus is dead. That's crazy. Now the chemicals we really want to worry about, ribose, this component sugar in RNA, and the two really big sugars we want to get are ribose and deoxyribose because we have these two nucleic acids. One has this particular sugar base backbone and the other has this one. So we have to figure out some way to produce these inorganically if we want to have a really origin of life scenario that makes any sort of sense at all. And secondly, we want to look at the types of amino acids. Here's all 20 thrown through here and their names. And each of these guys, and there's just 20 chemicals here, but each of these guys is coded. And so we know that we have on the DNA, we have these various ladder rungs that have a specific chemistry, and by looking at numbers of these together, we code out for these. And so you can, in the genetic code, then tell an RNA to build a protein, putting this series, this one, and this one, and this one, and this one, and 5 of this, and 7 of this, and build a protein. So that's really the basic tenet that Watson and Crick worked out. It's the miracle of life on this planet, and it works. Let's go to Mars. Let's find life. And if we find life that doesn't have this set of DNA and this code, we have found aliens. And that's the greatest hope. As we get there, we tear them apart, we simply look for the codes and the amino acids they make, and hallelujah, if there's any difference at all, if there's 19 or there's 21 or even the code's different, it's not Earth life. Or it's highly evolved Earth life. So what did all this stuff happen? And again, this is one of the really fundamental aspects of science today. When, where, and how. And how else? And what else? So these questions become really drivers. And they're drivers of astrobiology. They're drivers of evolutionary biology. We know when. We kind of know when. We think the origin of life is somewhere in here. The problem being, we don't have any pristine rocks on the planet in here. And the rocks we have from here to here are so cooked, trampled, ruined, mashed, destroyed. We talked about plate tectonics is so important for life on this planet, but plate tectonics has made being a geologist a very difficult process. It takes rocks and smushes them down into the crust and turns them into different kinds of rocks by heating and pressure. So to find rocks, anything in this range is rare. And this is really rare. There's only a couple places on the planet where we can find rocks older than 3 billion years in age. And so our idea about when life first formed is highly colored by the fact that we have very poor sampling. Even the best samples have already been heated and compressed. They come from Greenland, the Isua rocks. Our Earth today looks like this beautiful blue planet. We've got all the water. We just think, oh, yeah, look, that's what Earth is. That's an Earth-like planet. And yet, were we to go back in time, we wouldn't find these continents. We would see an entirely water world with some island arcs coming up, a radically different atmosphere. You probably couldn't see through it. There's no oxygen, different gases, lots of methane, and it may have been reducing. Here's a picture of what it may have looked like. The moon was a lot closer, and this picture isn't quite right. The moon would have very few craters. If we're back far enough, before what we would call the heavy bombardment, if we're back 4 billion years, the big rain from space that I'll tell you about in a minute hasn't happened. So we've got a little bit of land and a lot of ocean and no life. So it's within this context somewhere we've got to find a place, an environment that will make life. So what did Darwin say about this? Always go back to Darwin. And Darwin said in a letter to Haldane, I think life must have started in some warm little pond. And that, just a letter, he never published it. It was in the letter got published, became the iconic idea about the evolution of life. And sure, it makes sense. We go to ponds, we see all this life in the spring, and the pollywogs are coming out, and all that stuff. It makes perfect sense this could be a birthplace for life. But is it really? I mean, the origin of life is 3.5 billion years ago. The planet has been around for 1 billion years before that. Could life have gone way back to this? May have. There may have been a lot of stuff going on in that first 1 billion years. And that's the greatest mystery, and the one that's going to be the most difficult to decipher. And yet absolutely necessary if we're going to figure out how life really did come about. Nevertheless, the fact that we do have it, when we start seeing rocks, we see evidence of life at 3.5. Is this evidence that it's easy to make life on an Earth-like planet? Well, that's the assumption that's being made today. Life didn't occur 2 billion years ago or 1 billion years ago. It's pretty old. Now, where did it come from? The old idea was it was primordial soup. Terra firma, but there wasn't much terra firma. That's wrong with this slide. It was oceanic primordial soup, and that if we'd gone back, there was the ocean, and it was full of this gooey, organic, sludgy stuff, and that somehow it just sort of wiggled together, and boop, out pops the first life out of the soup. The warm little pond was where the soup would have been, but the problems with that are many. There's a huge high ultraviolet flux, because our sun at that time was a nasty bugger, and there's no oxygen. What saves us from so much radiation from space is ozone. It is a form of oxygen up in the atmosphere, and it screens us. And we know the holes in the ozone layer now that occur over South America and occur over New Zealand. We've got the Kiwi in the front of us, and the Kiwis now at school require their kids to wear hats. Isn't this true? I was in New Zealand, and there's a hat rule. I love wearing hats now as I go increasingly bald. Hats are wonderful things. But the kids have to do it because they are being bombarded. They've lost their ozone, and they're losing their ozone because of fluorocarbons going up. You also need energy, and you need component concentration. So a warm little pond is a bad place. Energetically, that place for formation of life may not have been good. So what are some alternatives? So if not a pond, the one that's really been available to us as the favorite since '77 are hydrothermal vents. These areas in the deep sea, we saw pictures of these a couple lectures ago. These are areas plate tectonically where we have heat, volcanic activity coming up. There's hot water bubbling up. It's bringing up minerals. It's producing areas of life, but really staggeringly interesting sort of reverse stalactites. You've got big chimneys that grow around these hot vents of material coming up. There's bacteria around them now. And back in 1977, John Barrows and others seeing these vent faunas for the first time on one of the first submarine rides down there where the vent faunas were discovered, suggested maybe this is the origin of life locality. And since then, there's been a lot of work on this. I noticed that John Barrows of the University of Washington last week announced that he found the oldest nitrogen-fixing bacteria that's an extremophile. Nitrogen fixation is a really ancient metabolism. And he's found a nitrogen fixer that lives at 95 degrees centigrade. So this is a huge breakthrough. The problem now is too much energy, and it fell to the father of the Miller-Urey experiment, this great experiment we talked about yesterday where in 1953 Stanley Miller of the University of Chicago and his advisor Harold Urey created amino acids out of some very simple chemicals and showed that it could be formed inorganically. You could build amino acids. But Miller heard about this, the vent is where it happened, and said, no way. So here we have vents, and here we have some of these cool chimneys, and all this stuff coming out of here. There's mineral species coming out of here, but there's also bacteria being blown out of here. Now, in some places it's too hot. The bacteria aren't there, and the stuff comes out, and the bacteria are just growing around the edges, sort of blasting around through here. But all this white stuff is called snow. That's all bacteria. Bacteria that has come blasting out or living close, a few animals through here, but this is all snow. And the snow are huge aggregates of snot, if you will, bacterial snot that just cover these rocks. Enormous amounts of biomass growing on around because of the energetics. There's food available coming out of these things to these bacteria. And Miller said that is the problem. And the problem, he said, is that RNA is a really weeny molecule. It doesn't cook well. I know about cooking. I have attempted in my life several times to bake a cake. And I know several of you have had my experience. It goes in, you cook it for a while, and if you cook it too much, if you have frosting or any sugar in there, what does sugar do if you heat it too much? It goes from this wonderful stuff that we all love to this black, tarry, and it tastes bad, and it smells bad, and an overcooked cake. And that's what Stanley Miller said what happened to the sugars down there. The RNA sugar got too cooked. Stuff breaks down so quickly in this environment that it is not believed by these guys. The intense heating must so readily destroy stuff that you could never produce all the chemicals you need to put this stuff together. And a lot of people suggest they're right. You can have life down there, but it sure seems hard to make life down there. Another problem is being the chemistry itself. There's this pervasive left-handedness required for life. Heating destroys it. Unless you're on the very outer edges. But if you're on the outer edges, you have another problem. You've got to concentrate stuff together. I mean, you can't just have it spread out in the cosmos. It's got to get stuck together. I've got to have that chemical over here and over here, bring them together to make life. So how about a desert? And this is where new stuff is coming about. And this is a highly interesting new point of view. Deserts do things. You know, if you put some water in the desert, it evaporates away. So you can get concentration. That's a problem. You can get energy. There's a lot of sunlight in deserts. There can be minerals in deserts. And it turns out that a NASA astrobiology group led by Steve Benner of Florida discovered that you can produce ribose if you have a particular mineral. And the mineral that he had is one that was very famous and beloved by me as a child. Now, many of you probably first knew Ronald Reagan as a president, but I knew him as the old ranger on Death Valley Days. Somebody here must have seen it. And what was the sponsor of Death Valley Days? 20 Mule Team borax. And in my first chemistry set, we used to play with borax and make borax crystals. We had a little round thing and stick it in and make a little borax. And then we go home and wash our hands with the borax soap because my mom had tons of 20 Mule Team borax around. Borate minerals don't like water. They love deserts. Benner started playing with borate minerals, and lo and behold, it stabilized this ribose stuff. It helped him make ribose, sugars, at temperatures and chemistries in ways that no one figured out how to do it. It came out in 2005 in Science. Huge breakthrough. But where could you find 20 Mule Team borax? Well, the ancient Earth didn't have many deserts. You had a few islands out there. So here's another problem. We found a way to make it, but we don't seem to have any place on the Earth to make it, which led Joe Kirschvink in the Carl Sagan lecture a couple years ago to suggest that we're all Martians. Because at the time that Earth had all these oceans, Mars had a small ocean and lots of deserts. And we know Mars rocks make it from Mars to Earth. And ergo, according to Kirschvink, we are all Martians. I tried to sell this as a book, but nobody would buy it. This is complicated. It's from Kirschvink himself, but what we're going to do is we're going to start out with some chemistry here. We start out with, in this particular case, an organic molecule. Here's formaldehyde we've heard at, and we start without borate. We turn brown tar. Brown tar is what I make when I cook cakes. Ew, it stinks. It's horrible. No life there. But if you put some borate minerals there with borate, in fact, you can produce this borate complex, and if you keep cooking, lo and behold, you get a whole series of sugars, including ribose. It's a complex step, 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 and then you get the stuff you need. And if you take the borax minerals away, you don't get it. This is a major insight into how it could work. Did it happen this way? We don't know. But it's better than anything we have yet. So this is what people are doing. It's at this level. They're piecing together bit by bit by bit by bit. Now at Harvard, of course, we have this Origin of Life Center, and they're making little bits of RNA. They call them aptamers, and they're making these aptamers evolve. And they're stringing together bit by bit by bit, and they start grabbing amino acids, and they can start building proteins. Jacques Szostak does this. He's 20 years into this. And increasingly now, they're getting better and better and better. And this group bets. Szostak said, if you give me 10 years and $200 million, but I'll do it in 5 for 20, I'll make you artificial life. Harvard said, we call your bet. And they're giving him the money. They gave him the center. He's bringing in everybody who knows anything about this. And they're building it right now as we speak. So where did life begin? Deserts, but not just deserts. And here's another insight here that might be really cool, because not only do you need a desert, there you are in your desert. Well, these guys are doing this in these flasks, and they're like, if you've been in chemistry, you know, you've got all the beakers, and you've got the filters, you got all the stuff, right? You need an organic chemist and an assistant and a washer and a bottle washer and all that stuff. Well, where do you find that? Well, you need natural beakers. You need to have liquid with minerals in it evaporate away. You need to decant it, you need to filter it, you need to do lots of stuff. And it turns out that if you have a series of impact craters on a hill, you can do that. Theoretically, you start with one concentration, groundwater goes down, pulls out to the next crater, water hits it, it gets all chemically concentrated, down it goes to the next. The world was covered with impact craters. So this is work coming from MIT, suggesting that impact craters themselves were probably the place where life could have, through this borax system, worked. So this is pretty cool. This is the last 3 years now. We're out of warm ponds, and now we're into old rangers and Mars. I don't know if that's progress or not, but it's very cool to me. So the impact craters, of course, is making the RNA the hardest part, that we have to have serial evaporations. We need a desert to do it. We don't have glassware, hence the craters. So then what happened? Well, then what happened is life finally gets going, and as soon as it gets up in its own two little tentacles, it starts getting whacked and whacked and whacked and whacked, because from 4.2 to 3.8, the Earth was bombarded. And how did life survive? And how it probably survived is by going underground. Some of these impactors were so large that they evaporated the oceans. And I would suspect that anything that could evaporate the oceans would kill all life, because all that goes into the air, superheated, and it acts like sterilization of the entire planet. And it rains out after some hundreds of thousands of years. So any life in that ocean, of course, is killed. So the only way to survive is life is going to work its way down in the rocks. And that's why we're so interested in seeing life in a rock today. We talked yesterday about one of the great astrobiological findings is the discovery of bacteria in rocks. So you could cauterize the Earth, but if it's down, you don't have to worry about it. Deep ocean vents, deep in the rocks. These are the places where life may have moved to survive this early Earth. And here are pictures from the Hanford Reservation. These are fluoresced. Each of these red things is a bacterium in rock. And here they are in the thin section. So there's plenty of them down there. There's lots of life. So was it a soup or was it a zoo? And here's where I really suspect that we didn't have, as Darwin thought, finally something gets together, life forms, and off it goes. I think we had hundreds of millions of years of near life, sort of life, almost life. I've got everything but this. And then a lot of stuff borrowing from others. And I think this is a much more reasonable way to think about it. There's a zoo. Lots of membrane types, lots of genetic systems, lots of metabolic systems. The greatest diversity of life on this planet, I submit, was 4 billion years ago. And we've had less and less diversity of life. We have the lowest diversity of life, one kind of life on this planet, unless those other aliens are here now. And back then, it could have been thousands or millions of kinds of life. We've got it all wrong. We get ever more species of one single, simple, stupid mode of life. It gets so boring. But there had to be, getting to our kind of life, one prior kind of life, RNA life. The way to get to DNA has to have gone through RNA. We know RNA now does certain things, but we also know it's capable of self-catalyzing. This is always the problem. You needed metabolism, and you need information. Well, here's a molecule that can do both. It can serve as a catalyst for your chemical reactions, at the same time holding the information you need to tell things what sort of chemical reaction to do. Stanley Czech won the Nobel Prize for discovering this in the 1990s. And this was another great piece of the puzzle, trying to figure out. So the earliest life might have been a simple, naked strand of RNA, a little piece of RNA sitting in there. That could have been the first life. And the question then is, how did DNA take over? And there's a couple of models of how this could have been. This is what I teach in my course, that we had a first primordial form down here, some extinct lineages. So here we have two. I'm saying there's 1,000 or 1,000,000 or who knows how many. But then there is a takeover, and we call this the most recent common ancestor of all things. This is where Darwin starts, right here, his diagram. That's it. But even in the textbooks, we know there's a whole lot of stuff happening before that. It wasn't just non-life and here's first life. No, there's got to be a lot of kinds of life, a huge diversity of life on Earth, leading to this takeover of one kind of life on Earth. It's a sad story. Increasingly, we know that early life, instead of doing their own thing, were indeed swapping genes. And this is from Doolittle, a picture in Science, called lateral gene transport. So here's various groups of bacteria. And here's this idea of how everything happened. They're taking pieces of genomes and plugging them from one to another, stealing from somebody else. So early evolution isn't a line here and a line there. It's this octopus tangle. So the early days, it's really hard to know what you call a species and what you don't. But what we have of it now and what we teach is that it all sorted out when all the dust fell, when everything's over. Here's that most recent common ancestor. We get this very nice, simple tree, the three-part tree of life, and the great discovery in the 1977 work that we'd have not kingdoms anymore, but a higher category than kingdoms, and we call these domains. The domain bacteria, the domain archaea, and us, the domain eukarya, and we put the kingdoms, these are the kingdoms on that. It wasn't so long ago, a book was published called 5 Kingdoms. So this is what the revolution has done to that now. So 3 great divisions of life. Both of these look like bacteria, archaeans and bacteria. The great discovery of Wu's in 1977, of course, was using RNA work to show how different these really were. That this group is as different from this group as they are from this. And so this, hence this 3-part division. And I decided this doesn't work. And I don't think it works the big assumption, if you admit that viruses are alive, there's no place to put them on that last tree. But even if you don't admit they're alive, if life came from RNA, there's no place to put that on the tree either, because every part of that tree is a DNA organism. And so I decided we need something higher. If we're going to have a tree of life, we need a higher up division. I call this a dominion. And so this is the tree that I published. And this is the tree of life that you just saw. And here's all the other stuff over here. RNA life over here, RNA viruses, and RNA life. Just because it's extinct doesn't mean you can't classify it. No paleontologist ever thought about the history of life, so they didn't think about the extinct stuff. And so once you admit that there was RNA life, the tree doesn't work. And the whole thing I call an arborea, hoping that there will be another tree out there. There's more than one tree. And so the way all this happened, each of these pieces then is an evolutionary event, an advancement to get to that. But there's a lot of stuff that had to happen to get to that. So variable kinds of life then. We've got the stuff we talk about, life. But how about non-DNA life? Does it exist? What does chemistry say would be permissible? And what might be permissible is a different information system, a different solvent, and a different membrane. So the way we can make an alien life, if that's true, is we could first change the nature of the information system. Different type of DNA. Secondly, you need a solvent. You need chemistry to work, and chemistry needs a solvent. Change the solvent. We are water-based creatures. If we could find an ammonia water creature, or a hydrogen peroxide creature, or a sulfuric acid creature, all these are solvents, that would really be an alien. And finally, as I suggested, we really don't know if there isn't some different type of life down there. And I'll tell you why it's so simple to recognize that. How you recognize life, you know what you do? You use a DNA test. And if it's not a DNA life, it's invisible to you. And that's what's so hard about going to Europa or to Mars or anywhere else, is we're going to take our DNA paternity tests to these places, and they're not going to work. So we have to cleverly figure out, how do you find life that's not DNA life if all you have is a DNA test to show it's alive? So water, 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 water. And here's where the weird life people start thinking about where things are just weird and things are really weird. Water, between a 5 pH to a 9, DNA still acts like DNA, but if you go below 5 or above 9, lots of cryptarians don't work, things are really strange. So within this range, we can maybe think of alternative nucleotides and different stuff, but it's not that weird. No, to get to the truly weird, we have to get to some other conditions. And these are really weird. Life that doesn't require carbon. All life on Earth is carbon life. Or life that doesn't have the stuff that we use, RNA world. Believe me, RNA world, RNA life would seem really weird to us now. Life that does not require certain metals, this would be weird. No Darwinian evolution, that'd be really weird. And these are the directions that scientists are thinking to explore as what alternative life might be. Now we know, again, we have to go to Star Trek to figure everything out. How about life without matter? And here's Q. I was worried about that poor guy. I mean, he wasn't in that many Star Treks. Did he get all his money from those 7 Star Treks he was in? Was poor Q like desperately poor on LA streets, wishing for one more Q? But he was this. He was life without a boundary. And so we don't think that could be life. At least I don't. So let's take a quick rogues tour and ask, in our solar system, what might life be like? And it turns out the best place, the hopeful place, the place we want to get to most is here, Mars. What could life be like on Mars? But also we're thinking about the moons of Jupiter, we're thinking about Titan, and even Venus. High up in the clouds of Venus has been proposed that a very peculiar type of life, I'll show you in a second, sulfuric acid life, could theoretically be possible. We all know about Martian life. This is the ALH, famous little, he was green yesterday, he's back in his normal black and white here. And there are periodically discussions about more new evidence about life from a meteorite from Mars. But certainly this is where we're going to put most of our money to look for life in the solar system. Mars being further out, colder, and yet we can imagine down in the subsurface, if there's some geothermal heat, some of that ice that we know is there is melting a little bit, we have water. And we have hydrogen. If you have hydrogen and you have water, you could have our kind of life. Many bacteria from Earth could live on Mars today, and that could be the problem. My biggest nightmare is we go to Mars, David Smith, are you here? David Smith might be, there he is. He's a Princeton undergrad who might be the first on Mars, and I hope he is. Gets there, pulls it up, and it's exactly identical to Earth life. It's a bacterium that's got everything that our bacteria have. So what are our possibilities? There's only one way to make life. It evolved because it's totally separate from us, but it evolved everything like our life because that's the only way life could work, and that's a possibility. 2, it's Earth life. Some big asteroid hit the Earth, threw a rock from space, and transported it to Mars. That can happen. 3, all life started on Mars anyway, and this is just the mother life, and then we're just coming back to see Mom. Or 4, those cheaper, faster, quicker space probes that we dropped in the late 90s dropped a bunch of bacteria that colonized Mars. That's the scariest one. We don't know if it's not Earth life. That's why we hope the best solution is it's different. It's so chemically different, it can't be Earth life. Because if it is Earth life, we got those 4, we'll never figure out which is which. And that'll be really frustrating. So what if we go further out? Here things are really strange. We're in Europa. It's all frozen and icy here. Here we would have to have life. Any Earth life would have a really darn hard time living on this place. The coldest life on the planet lives in ice. It does so by secreting mucus around it. It can go down to about -40 centigrade is the record. And that's amazingly cold. Most Earth life dies off at about -2 or -3 centigrade, most bacteria, but there are a few. Jody Deming has now found some really cold lovers. But even that isn't anywhere close to what's going on here on Europa. And so if you want to be in Europa, or if you want to be in cold, you want to do some different stuff. And so some more chemistry here. Again, we have to have a number of solvents, and here is what we do on Earth. We use water. But if we're in a really cold place, icy moons, ammonia might work. Ammonia is a great antifreeze. If you could figure out how to have water in your cell, but a little bit of ammonia too, that doesn't screw up all your cellular machinery, you could make a living in those planets. And it seems to me theoretically possible, and I've been asking for genetic engineers to see if they could demonstrate this, and all I'm doing is copying Sagan, because he said it 20 years ago. He said, let's see if we can make a bacterium, an Earth bacterium, that can survive if we could manipulate the genome sufficiently to allow it to live with a little ammonia as well as water. We could demonstrate at least it's possible. It wasn't possible in his time. We have the tools to make it possible now. And the final type is warm, Venus. H2SO4 is your solvent. And here's a way now you can think chemically. This is from Steve Benner. These are highly possible ways that we could imagine life could live with different solvents. And this one would surely be alien in anybody's estimation. But the final wonderful dream is Titan. And here we are again on the Louisiana coastline, and we're coming down on it. There's the Mississippi, and here's the Delta, and there's New Orleans. And as the lander, this is Titan. As the Cassini made its way with Huygens probe coming down on this, we're entering a world where organic chemistry is king. And if there's life up there, it is going to be alien. It's going to be so alien, and yet there will be so many lessons to learn. And again, I would advocate we skip Mars entirely and go here. Take our species to really get a hard task. You go to this place and do some chemistry and look for life. Because who cares? If Mars life is going to be some stupid bacterium that might be really close to Earth life, but here you're going to have some cool aliens. I mean, this is worth a movie. And the cool aliens, again from Steve Benner, might be using structures like these. And here's the final dream, folks, of science fiction. This is true silicon life. But it's not true silicon all by itself, because what do we have here? These are carbons. So here's the carbon group through here with a long chain here. Carbon in here, and a silica here. At our temperatures, I mean, let's face it, mica isn't a very cool stuff. Mica is a silica sheet mineral. If you're a silica life, you can think of being all crystalline. You're not doing a lot of 40-yard dashes or anything. You're just... Now, this stuff at low temperatures has a whole different chemistry. And you could be structurally competent with the types of structures. You can make membranes of this stuff. And so here now we're seeing the first dream of what silicon life, instead of nonsense silicon life, but real silicon life. And again, from a group, NAI group, looking with these and putting them in chambers at very cold temperatures and studying the behavior of what could be, these could be, Titan organic molecules. Implications, ethics, and dangers. The thing is, we've already made aliens. The alien I told you about already with the 21st amino acid. Should we? Well, there's some ethics there. Why do it? What could happen? What could happen? The trouble is that I would suspect that the scientists aren't the only people who have made aliens. The Department of Defense might have actually some very good uses for killing humans with aliens. If you start manipulating germs in certain ways so that they are not exactly Earth-like life, they could be highly detrimental to Earth life in certain particular fashions. I don't know if this is happening. I wouldn't doubt that it's happening. So where do we go from here? The other aspect is, what do we bring home? Don Brownlee, a man I dearly love, truly, got the get out of jail free card for the Stardust mission, which had just landed a year ago in the Utah desert. There was no containment. There was no go into quarantine. There was no, gee, maybe there's an alien bug like the Andromeda strain that's going to take over the planet. There was absolutely no planetary protection for Stardust. They took the stuff out in plain atmosphere. They didn't worry about germs, because NASA considers that coming from anything like this, an icy body like this from out near Pluto, would never have the potential of life forming. And I would submit that that was not probably the smartest thing to do. 99 chances out of 99.1, you're probably going to be okay. But we didn't know. We used to take those Apollo astronauts and quarantine those poor bastards. But this rocks from space we brought home, we didn't do anything to. So there are, if life is more pervasive than we think, and if aliens can be produced in ways we don't know, if we produce an ice-loving microbe like I want to do, and it escapes the lab and takes over Antarctica and loves Antarctica and starts killing all of the Earth life in Antarctica because it outcompetes it, is that a good thing? Probably not. So I want to finish up. I want to think about forest of life. These are the arboreas that we have on Earth, carbon-based. That's us. Here's our tree. On Mars, probably the same sort of stuff, but Europa and Titan, probably non-DNA life, probably non-water solvent life, and certainly Titan. Oh, this is Europa. Titan itself, non-DNA life, non-carbon-based life. And my hope is there is life in the solar system. We get out there and see it. I mean, I'm really hoping we get to see all kinds of cool life out there. And the final point in this lecture, I promised I would do this, I don't really want to, is the sense that, is our universe special? Is there a special recipe? Well, we know what a universe needs. It's got to be very big with lots of particles. There's huge numbers. It's got to be long-lived. It's got to have gravity. It's got to have all this stuff. But there's a group of people that have suggested that what we see out there seems almost tuned, specially tuned for life, and this has a name. There are some things about our universe that are curious. For instance, Q, the measure of the cosmic texture, it's got to be able to expand so we can have ripples. If we don't have ripples when our galaxy was part of the Big Bang, there'd be no structures in the universe. If there's no structures in the universe, there's no galaxies or stars or anything. I mean, here's a number that has to be sort of just right. We've got to have some balance going on in stars, or we don't produce the elements. If they're weaker, if they're stronger. And so this has been used to do something called the anthropic principle. In 1974, Carter suggested that physical constants must be within a very narrow range to enable life as we know it. And the universe appears to be fine-tuned, he said. Well, fine-tuned, who tunes things? Tuners do, piano tuners, people tune. Now, was he saying that some conscious life tuned it, or did it just sort of get tuned by some dead tuner? But from that, there has been a huge literature that's gone out, and a big debate back and forth and forth and back. We have even Hawking weighing in about the weak anthropic principle, as he said. And here's his quotes. And this has been seized upon, of course, by the intelligent design creations people. See, we were designed to be just right. At the moment, it's not really science. It's not testable. And if you can't test it, it's not science. So this is out of the realm probably of what we do as scientists, but it still sits there, and books are written about it, and it's uncomfortable to scientists because we can't test it, because we can't really get our head around it, or at least I can't. We have something from Barrow and Tipler in their famous book, The Anthropic Cosmological Principle. And have you ever tried to read that book? I have. It's about this thick, and it's like reading the Philadelphia phone book. I mean, it's numbers and boring prose, and numbers, and near chapter 18, and these guys are so smart, and I have no idea what they're talking about. But anyway, this is some of what they say. Intelligent mind observing, blah, 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 blah. So that, I'm done with that part. So let's finish up. The variable histories of life, because I'm not smart enough to figure out those guys. Variable histories of life, a planet forms, life doesn't evolve. Or it evolves, has a history and dies out, or it's exterminated and re-evolves. So there's a whole series of things here. You just go through them step by step by step. And I think this is the way we need to approach habitable planets in the universe. This is what could have happened, and this and this and this. And histories happen. And life doesn't have to be the same kind of life. There could be multiple lines. Just like, I hope there is aliens on this planet. How cool would it be? Time magazine, and here's some other like bacterial-like thing. Non-Earth life. 27 amino acids. Different code. Looks just like a bacteria. That'd be so cool. Sometimes planets, I think, if you don't get life, you screw up. This is the work I did with David Catlin. We started thinking about nitrogen, what happens. If you have an ocean planet, if you have an atmosphere full of nitrogen, you throw lightning through it, you can start stripping the nitrogen out of an atmosphere, and it goes into the oceans, it precipitates down there. Unless you have bacteria to put it back in the atmosphere, you start losing it. And if you lose your nitrogen, it'll get replaced by carbon dioxide. And this may actually be the fact that if you don't get life, you won't. And so this is actually another new area of research that we're starting to look at. Well, the final part is that funding in astrobiology has been sliced in half by order of the Bush administration. We're talking about this today with students and with professors, and I think it's just a blip. And I do think that someone in this room could or should go to Mars. We're close. And I want to finally finish all these 3 lectures by thanking my hosts and thanking Princeton. You are so lucky to be here. This place just crackles with intellectual energy. I hinted at 2 high Deanie type people. I'd love to have a job here, but they nodded sagely. And this is where I have to go back to. Thank you. As always, I'd love questions.
We have students who are going to be passing around these microphones, so wait for the mic to come to you, and here is one microphone.
I love this hat. That's good. You know, this is a Princeton. This is the Princeton astrobiologist. The Tigers, right? Isn't it orange and black? Okay. Question, please.
I have a question. So, this is on? So, do you know anything about the distribution of borate in our solar system and beyond? I'm curious because the Murchison meteorite, you may know, has a little ribose in it, or ribose and its relatives. So I'm assuming that there are alternative ways probably to get ribose too. But
I don't know if there's any borate ever found in a meteorite.
Okay.
Because it
or
would
if it's
be,
been looked.
if we're on a meteorite, it hit, as soon as it gets rained on, it goes away. So if there's any hydration whatsoever, it's not going to be there. I'll find out, though. I mean, that's a great question that I don't know. But it's just such, borax chemistry is now just a hot thing. It never used to be. Yes, please.
Why isn't Hawking's explanation the simplest and it makes sense? Look, the Earth has won the cosmic Powerball lottery. That is to say, if you think about a lottery, let's say the chance is 1 in 100 million. Someone wins it every year.
I've used that same argument. That's what I used to say in rare earth. This is my only hope is that this is just...
It has nothing to do with intelligent design. It's just...
Well, my sense, too.
It's a lottery.
I don't advocate any intelligence in this thing. I totally, completely agree with you. But it's so easy for people to point it at unlikely events and say that it's unlikely, it's not impossible. And yet it can be seized upon. I know. That's why we've got to go look.
It's the statistics of large numbers here. You always find one fluky event.
I totally agree with you, but I'm uneasy simply because it's so easy to be misused and smashed over my head, which I hate. Another question, please? Please?
Mentioned that viruses aren't a life form, but somehow I'm really getting stuck in my mind about HIV and how old viruses are and how they evolved.
They are life to me.
Right, exactly, because HIV is
it evolves quick. It does everything.
Right, exactly.
Think of Giardia. Giardia, when it's not in your body, is this little cysty thing, and it almost technically, from many points of view, it's not alive. And then it gets in, it gets hydrated, it pops in and kills you. Well, viruses do the same thing. It goes back to Lynn Margulis, because she said all life has to be cellular, and she made that definition, and she excluded viruses entirely.
Yeah.
And I just think it's just from a common sense point of view, it makes no sense to me, and yet we teach our biology kids they're dead.
Right, because, HIV can completely destroy the cell.
The other thing is, if a virus is alive, you have to put it on the tree, and there's no place you could put it, so you have to expand the tree, and then you've got to reprint books, and that costs money.
Please, okay.
We're talking about the practical points of view here.
I just needed to acknowledge viruses.
Think how cheap it would be if no scientists ever learned anything. We'd never have to change any textbook. We'd keep the same forever, and the trees would never die, and it's a better system, right? No. All right. Next question, please.
I read a book several years ago, or many years ago, and I forget the name of the book, but it's by a biologist who explained his theory of how life began. And he said, well, if it didn't come from another planet, his key point was that you had to have a membrane. And he said you could not have life begin in the ocean because you could not, where would the membrane come from? And he said his theory, he went through the whole science of how it went through, but his point was the first life cell had to be a droplet of water. And the whole idea was it had to be good conditions for that to happen, because droplets of water, if you have the right conditions, they can combine and switch, all the chemicals. And so his theory was perhaps at a cave where you have sunlight and you have water dripping down, little droplets of water hitting rock, and there you could have over many, many years. Perhaps that's how you got the minerals, how you got the exchange of...
Sure, that's as reasonable an explanation as any I know, but an even better one, instead of drops of water, are soap bubbles. Go to the seashore and you see that scum from the waves come in and splash and it makes little bubbles. Well, bubbles are great sort of protocells. And if bubbles are now made up of enough stuff and they don't pop right away, if they're sitting in a liquid and floating around, they can pull stuff into them. So there's a guy named Dave Deemer who builds protocells out of little soap bubbles, and he's made beautiful little pseudocells. People are working in two directions. They're working on building cells without anything in the inside, and they're working on the inside stuff, and then you have to put them in cells. Well, that's what life did. Dyson here, the great Dyson, suggested a long time ago. That's what happened. Metabolism evolved in one set, and on the other set we had somebody who had information. So when metabolism married information, life formed.
Thank you.
But your method is as good as any. Question in the front here.
I'm referring to your tree of life, where few survived, many that disappeared.
Mm-hmm.
And 2 days ago, a question was raised, why theory of evolution evolves in such an extent that species disappear. Namely, they evolve themselves and extinguish by themselves. I'm not referring to a catastrophic. Now, using what you just said about the onset of life, why cannot we say the same kind of probability it happens after so many hundreds of millions of years? They made a mistake and therefore become extinct. By the same probability, they made a correct choice, so they become life. Instead of what you said, they become rare.
Well, mistakes can be made, certainly, but quite often you didn't make a mistake, but the world changed around you. and there's no longer any ability for your possibility of existing. And it changes around you by better stuff evolving, or just the Earth was so rapidly changing. I mean, one of the greatest mass extinctions on the planet is something that we all needed to have, the oxygen revolution. When finally first plants started producing oxygen, it killed off almost everything on the planet. Totally anti-Gaia. I'm trying to sell that book, Anti-Gaia. He's not buying it. All right. I think Gaia is totally wrong. I think this is absolutely, completely wrong. I wish it were wrong. I wish Mother God would take care of me, pick me up, carry me off, feed me, bathe me, take care of me. No, I got to walk home. It's cold outside. Question, please.
I'm a little confused. Yesterday in your lecture, you told us about the habitable zone, and it was like just confined to the Earth, just about. And today you tell us about, there might be life on Titan and so on and so forth.
No, see, I think the habitable zone, what I tried to say yesterday, I never want to look at the tapes of this. I'll just realize how bad I was. I tried to say, my interpretation of the habitable zone is the habitable zone should be the animal habitable zone. That's what the Earth is in. But then I tried to say that microbes, I think it's a nonsensical concept. When you deal with microbes, they don't care. They don't care.
So all that you're told us about today, this, in your opinion, could never evolve into something more complex like animals?
Yeah, this is all about microbes today. We never got beyond a bacterium because I think that's what the majority of life, that's what we ought to study. I mean, finding animals in space, I think we may never. But I bet we find lots of microbes in space. I think we are rare events. If I didn't think so, I'd be kicking my co-author, and I can't do that. A great question, though. I mean, it drove me crazy when I was writing Rare Earth about habitable zones. I said, this makes no sense. And yet, in the literature, it's ingrained, it's ground truth. That's stupid. If you're in Titan and you've got these conditions, you could be a bacterium perfectly well, and you start convincing yourself with this chemistry it should work. You're not in the habitable zone. So why do we have the stupid concept? Malcolm Hart made it in the 70s, and it's just been, holy grail in astrobiology. All right, I got to stop. I'm seeing my editor look at me. I'm getting the look. I understand. Next question, please.
Well, I just had a question about Titan or something. I think there was just today or yesterday there was announced that there are lakes of methane or something, and I wondered if you might want to speculate anything about lakes of methane on Titan.
Well, lakes of methane to us, lakes of methane were where you would find and suspect to find these silica carbon systems. In a lake of methane, it would be a good organic compound. So this is the stuff your cell would be made of. You still have to get information, you still have to get metabolism, who knows what that is. But, a few years ago you would have said, well, there's no possible way. Carbon chemistry can't work on Titan, therefore there can't be life on Titan because we're such chauvinists about carbon. But once these great organic chemists, I keep going back to Steve Benner, he's so great, and he sees these problems and he goes and solves it. He spends 5 years and he figures out the silanes, which have been known since the 30s, would work in Titan, and he's totally correct. And so it gives me hope that we as a species explore this solar system all the way from Mercury all the way out, hit to every body on it and look for life.
Excuse me, I was wondering, you mentioned something about life conceivably existing without having natural selection operate on it. I was just wondering, how is that possible? I mean, once you've gotten basic life, how can it develop if not by Darwinian natural selection?
I have no idea. I stole that slide from the National Academy meeting on weird life because I thought they're trying to figure out life that's so weird, and that's so weird. I mean, to me, that's as weird as Q is. But these guys, we were tasked with trying to think outside the life box of Earth. And so a lot of what I've presented tonight comes, of course, I'm standing on great shoulders, and these are from many brilliant men and women who came up with some of these ideas. And I just wanted to try to give you in a lecture that I've never given before, some view of what could be bigger than what we see in the damn books.
Prions, do they fit into...
Great question. Prions, I draw the line at. Now, I wrote this book, Life as You Don't Know It. It sold 7 copies. And one of the people said, you know, you gave prions such short shrift. They're only given 2 paragraphs. And they say, if you think of a virus as alive, why are you being a chauvinist against prions? So I went back to my friends who know a lot about this, and we argued over it and haggled over it and talked about it, and I still think they're not alive. They do bad things, just like if you eat arsenic, it's not going to be a happy moment in your life. But the prions are more complicated than arsenic. I mean, they are complex proteins, and we knew they do horrible things, mad cow disease, and probably things we don't even know about are coming out of these. So, I mean, it's such a great question.
You would consider that information?
Excuse me?
The prions would be information?
The prions are information, but they're also triggering things in our cells that we don't yet quite understand how they work, what they're doing. And they're making more prions in some weird way. So this is a very scary, I wish we hadn't brought it up, subject. Because like so much else, I don't know. It's maybe their life too. And maybe my sense of Earth life is that we are all Cadillac life, even our simplest life. There's a great genius called Karen Smith who suggested that we could think of life as crystals. The crystals show some peculiarities that life shows too, and that we are very complex. This is all Earth life, and there could be simpler life. And all our life is big. What if we had life that was tiny, tiny compared to our smallest bacterium? Could it still work? There's a small life group that's just studying just that problem. So these are great questions. And it's so fun, isn't it? I mean, this is really, you feel like you're in an interesting subject. Even my 9-year-old says I'm on the right track here. Most of what I do is so boring.
Hi, I'm sorry I missed the first 2 lectures, so if I'm asking something that you've covered, I apologize. I was just looking at this as a sampling problem, because when you were showing the timeline and you were talking about how the samples are really biased towards the later thing, I mean, there's sort of different sampling strategies you could come up with in terms of trying to extract, you know, planets that looked like Earth would have looked like, you know, 3 billion years ago or things like that. And then you're recommending Titan and Europa. So that selection is based on certain criteria that seem to be, you know, environmental or physical conditions. And that always raises the possibility that your strategy is really creating a bias in, you know, the kind of results you're coming up with. So I was just wondering if you could talk a little bit about what kind of strategies are being discussed and what a bias would be from a strategy that you've suggested, you know, given this is all, we don't have the technology to sort of undertake.
And those are great questions. The one that strikes me is, I was with Chris Scheibe today. I don't know, do you folks know that Princeton hired Chris Scheibe? He's a great genius. I mean, he's a tremendous thing for Princeton to have because he is equally adept at national security. He was brought here to be a national security expert, a threat expert, but he's one of the world's best astrobiologists, and he's like full professor level at both, and how he keeps it. So we talked to him today, and he pulled out a 1997 piece of paper. He was the chief investigator on a mission, a life mission to Europa that would do to Europa hopefully what Viking was supposed to do to Mars. And they had this all worked out, and NASA was going to do it. And they were going to, it should have been in 2003, it was going to land on Europa. And it got canned. And so now they've asked him to come up again and become the head of the new Europa mission 10 years later. And he said, no, I won't do it. I mean, last time I put years into this, and you never did anything. But the problem with Europa, and I think part of the problem that Chris acknowledges, it's going to be really hard, A, to get into the liquid in Europa. We've got to get through the ice. But once we're there, a couple of theoretical studies have suggested that life very well could be there, but there's so little energy. You know, we're used to life in such unbelievable richness. There's 1,000 viruses for every bacterium in the ocean, apparently. And every bacterium in the ocean is surrounded by millions of friends in a thimbleful of water. We are just rich with life on this planet. But there might be a bacterium every 30 feet, every 60 feet, every half mile underneath Europa. How could you ever find it? How could you sample it? You never could. You'd never find it. And that's the big problem with a lot of these searches, is just sampling itself, is that we have to detect ways to find the life if it's there, and know it's life if we find it. And these are just daunting tasks. We'll be really lucky, I think, to find life even in the places where it might be, unless we really think hard. This is the greatest challenge intellectually that I think our species is going to come up with in the next millennium. It's going to take a millennium to explore our solar system. I certainly hope that global warming of Lecture 1 doesn't take us out before then. Or I'll have to start wearing black again.
Peter, if I could ask a follow-up question to that one. I wonder if the choice of these moons is driven by the fact that a suitable condition for life is thought to be the capacity to have high rates of chemical reaction. So I've read recently about the possibility, for instance, of, in addition to having water chemistry where molecules can collide and therefore react, but also films growing on surfaces. And the general idea being that in order for life to be generated, molecules have to be able to generate interesting chemistry.
Yes.
And there's a general necessity. If is that a general principle that's used for selecting these moons for searching?
Well, part of it is the life aspect, and part of it is the rocket ship stuff. Can we get there? Can we get a mission there? Can we conceivably get the hardware down to where the life might conceivably be? And we're not going for some of the really thick ice cover. I mean, Europa has lots of cracks. We can get through the cracks. But we're going to have a really hard time going to the moons outboard of Europa, so nobody's even suggesting it. There's no suggestion for any missions to go to Callisto or Ganymede. I mean, NASA's just, we're not going to do it. It's just, you can't get through the ice, so forget it. So that's an engineering problem. It doesn't mean we don't think there may not be life down there. It just means we can't get there. So you got the two things that are making the selections. The beautiful thing about Titan, it's got an atmosphere thicker than Earth's. You could parachute in. It's great. You could parachute in, and once you're there, you could balloon around, and you could airplane around. I mean, this is an amazing place. You can just come in, very thick atmosphere. You just do the same thing we do here. You have a glider vehicle, and you just come down to it. So we parachuted the mission that was there. The Huygens parachuted in. And this is a simple place to get to. Of course, no, it's not. The radiation would kill you long before you got there with current technology. But if we had a spaceship surrounded by water, and we had some brave, stupid people, and sent them off. I don't know, would you go if it's a one-way trip? Look at all these suicide bombers. The thing that kills me about Iraq is that so many people are willing to die. But shouldn't we just tell some astronauts, look, we're going to send you one way, you know? You're not coming back. So get a big battery in your radio, stay alive as long as you can, and keep sending the information. I bet you get volunteers. I should stop now. It's time to go.